Hello, my name is Jordan Ahern. I'm going into my final year in theoretical physics at Trinity College Dublin, and today I would like to talk to you about my summer research project in quantum inversion problems. Specifically, I will be using the model of a delta function potential of n scattering states. For an inverse problem, we have three main steps. So our first step is actually the output of the usual problem. So if we do a forward calculation, we're generally trying to gain some output. For a scattering problem, this output is often your transmission over energy. So this will look something like some sort of smooth curve, which we're bounded by 1 because it's a coefficient. This particular transmission looks similar to a single delta scatter, which you may know. Once we have our input, we are then going to apply some sort of inversion methodology to it. This methodology will be the main part of our discussion today. Specifically, we'll talk about methods of configurational averaging and of Monte Carlo methods, Markov chain Monte Carlo methods specifically. These two methods will present a number of benefits and disadvantages, which we will discuss, and we'll also show some outputs from these methods. Your final step is to be able to make a prediction about your initial states, or whatever states that actually produce this transmission. These predictions can take a number of forms. You may, if you're just interested in inverting, you may give specific values. So you might decide how many deltas there are, where your deltas are, and what the strength of your delta potentials are. If you can fully describe each of these quantities, then you have inverted your problem. But in terms of real-world applications, we might actually prefer to design a particular transmission. Something that does not necessarily have a starting point. We might just draw something we think is useful, and we're going to try and work towards some sort of principle that we could tell a company how they can achieve a transmission that suits their needs. This data is less useful in terms of specifics because that's difficult to achieve. If you're talking about the scale of quantum scatters, it's very time-consuming to try and place an impurity in specific locations. So it may actually be more sensible to produce some sort of distribution that they try to follow in order to get a good approximation of that curve. Now, before we can actually work backwards, we need to make sure we understand how to go forwards. Specifically, we need to look at what our problem is. So, solving a delta function potential for the transmission is relatively simple for a single case. So for one delta function, we keep track of the coefficients that enter and exit and that are reflected. So A corresponds to transmission and B to reflection. We then describe our wave function in terms of we determine a wave function for each side of our potential. K x plus e minus I k x. K is equal to root 2n over. This wave function is correctly, or it's well defined for all points except for x1. And we then define boundary conditions that must hold for this potential to be correct. So these two conditions are, one, a continuity across the boundary, so your wave function on the left is equal to the wave function on the right at this point. And secondly, we have a discontinuous derivative. So instead we're integrating only across the boundary. So we imagine a small epsilon and then we integrate our Schrödinger equation, time-independent Schrödinger equation. And then we let epsilon approach 0, follow that through, this disappears. You just build an algebraic system of equations. Solve that system, and then you find your transmission based on the ratio of what enters and what exits. So A2 over Y1 gives you your transmission. That is relatively simple. At a certain point, it's just down to how your algebra skills are. This becomes less simple for n delta functions. So now our system looks like this. Any number of delta functions at all, we still have to assign ingoing, outgoing, so on and so forth. And each of these points has a coefficient, and each delta function has a boundary condition. If you want, you can go through all that process for each delta function. You can solve your systems of equations, but the algebra is not feasible, and it's not something a computer will do easily for you either, because it's just messy. So we think about ways to reduce this problem. And in this case of delta functions, we notice that there's actually no potential in between each function. They're disconnected. So this tells us we actually only need to care about the change across each delta function. And in these sorts of cases, we use a method which is based around transmission matrices. So these matrices, which I'll describe as M, determine your transmission across each delta function one at a time. So I can translate, or I can define a specific transmission matrix which relates to each delta function. And this sounds no simpler. It doesn't seem like I'm reducing my workload at all. But in fact, all we need to define these matrices is our one delta potential. Our algebraic systems produced by these two boundary conditions actually grant us the coefficients of each matrix. All that changes is the position of the delta and the strength of the delta. So now we can define our system in terms of matrices which depend on specific quantities, so on and so forth. This now reduces our problem quite nicely. So we define the transmission matrix, at least I do. There's varying definitions. Sometimes you'll see it reversed. But I define AI/BI is equal to transmission matrix applied to AI plus 1, BI plus 1. So this means that the coefficients A1, B2 are equal to the transmission matrix M1 applied to the vector A2, B2. And then this just becomes inductive. So you can now apply this your whole way down. A1, B2 is equal, B1 is equal to M1 applied to A2, B2 equal to M1, M2 applied to A3, B3. Follow that logical reasoning. You then just have M1, M2, Mn applied to A n plus 1, B n plus 1. And then as a convenient trick, we can actually just say that there is no incoming wave on this side. So that reduces our final coefficient to a 0. And now if we define our collection of M, just a single M now, we have that A n plus 1, 0 is equal to A1, B1. All that goes to give us a nice way of finding our transmission again, this time for n delta functions. Here we see that an minus plus 1 over a1, that can be seen to just equal m11 so that is the squared reciprocal of the 1, component of the transmission matrix. And the transmission matrix is just a 2 by 2 matrix, by the way. Okay, so now that we have described how we make the forward calculation, we just have a linear algebra problem. Easily done with computers, takes no time at all to tell your code how to multiply a matrix and how to create a transmission for any number of systems. All you need to define is your position and the strength of each delta. And from this point on, we can actually get into the meat of the problem, which is inversion. And for all our inversion, we have a main inversion tool which we call the misfit function. So our misfit function takes the form of an integral over energy So if we look at this integral, we are comparing two transmissions. So for fancy T, I am describing what our goal transmission is, potentially. For instance, this can be any particular transmission, something like that. And then for a regular T, this is, say, our predicted transmission. So we've applied a particular inversion procedure and we gain something there. Our misfit gives us a quantity that tells us the match or the lack of a match between the two transmissions across energy. So this is just a handy way to give us a positive definite quantity that lets us define how good our system is, gives us something to compare against. And that will pop up repeatedly. I'll repeatedly be saying misfit, I'll be giving a misfit number, and I'll use that as a way of quantifying how well something's working. So just for clarity, misfit of 0, excellent means you have reproduced quantity. Unlikely to receive. Greater misfit, the larger the misfit is, the worse your match is. Okay, so our first inversion procedure or method will be known as configurational averaging. So in this setup, we're actually producing a large number of transmissions, just randomly configured. Like you can have some specifications that you want to configure according to, but a particular set, and you add all these together and you get some smooth average. So we can define this specifically, our average transmission, and then we give it some sort of notation. So this is for n deltas. Yeah, we'll stick with n for now. So this is where we're just telling the system produce m, where m is some large number, random configurations. And then we're just summing over each of these configurations. And that gives us this blue transmission here. Just a smooth line condensing all that prior information into one transmission. From that single transmission, we apply our misfit function. So the misfit between our goal and our configurational average. And then this gives us some sort of match. Something all right. The handy part is that you can apply this misfit very quickly. So if you're trying to find a particular quantity, you create a surface or a curve against that quantity. So if I say n for the number of delta functions against the misfit, we then build some curve here that attains a minimum. And we claim that this minimum is probably your actual number of delta functions, the number of delta functions that created your goal potential or your goal transmission. And we get that out of DCA. So say we have one line n equal to 1 and another line where n is equal to the other way around. Let's say n equal to 5 versus n equal to, oh, I was right, 5 and 1. So our goal transmission, something like that. So it's somewhat clear there that the configurational average for 5 deltas is a better match, just visually, than the transmission for a single delta. Configurational averaging, it's a fairly nice method. It's got a good few benefits, actually. It's very consistent. If you have a database of your configurational average, because you only have to run this once, which is potentially the biggest benefit versus any other method I'll show, where you have a large initial time cost to configurational averaging. You will just run your system for a while to create a different configurational average for not just your numbers of deltas, but also for different strengths, for instance. So to become more complicated, we might not precisely know what strengths our delta is taking, or even if they're all taking the same strength. So you can create a large database for different numbers of delta functions and for different strengths. And you can think of simplifications to this, like a delta function it doesn't necessarily mean much, but you could take a delta function that stands in for an actual imperfection. So if you can identify on some material different types of defects, so say a vacancy or a substitutional defect, so you're missing something or something different has been placed on your material, each of these will act as a scatter in some way. So you could imagine trying to define these in terms of delta functions, and you then have some sort of discrete set of possible strengths for your delta functions, where each strength corresponds to a different type of defect. So that actually reduces greatly the number of quantities you need to create an average for, because you can actually just limit it to what will actually be useful, what type of defects you want to look for. And then for each of those quantities that you add in, you create a higher dimensional surface. So this is handy, we can draw this easily because it's a single quantity. But if you imagine this is actually just a slice through a space of n quantities, and we're actually looking for a minimum over some high dimensional curve, that minimum will correspond to multiple quantities, and that gives you a fair bit of information based on your inversion. So yeah, so our pros: high initial cost, and then after that, almost instant. You don't even have to go through graphing things. You can imagine, because we have our misfit, eventually you get just a large database, and then you just take the misfit across all the database, and your minimum gives you some number. That's a quick way. It's not necessarily the best way of going about it. Doing that method, you lose some information. For instance, you lose the surrounding areas should be sloping downwards. That's something you see here, but you don't necessarily see if you just take a scalar from a database. So there's always more analysis to be done, but in the most simplistic form, this is almost instant forever once you put in the initial cost. The more times you use configuration average, the better off you are. You pay back all that time in time you don't spend later. Now there are cons to this. It's only an average. So sometimes you can have a transmission related to 5 delta functions that actually just follows down the bottom, or it's outside your standard deviation. So while that actually is generated by 5 delta functions, you might actually identify it as having 10. So that's an example of one area where you can have trouble. You're not guaranteed in any way. You're never going to be guaranteed for any of these methods, but outliers are going to be an issue. Additionally, the amount of information you actually receive back from configuration averaging, it's specific once again. So this is our point tree. It's how we predict our data. It's an excellent inversion procedure. You can invert fairly well and get back to a good guess. But you don't really know how your underlying distribution works. It's related to this problem again. This particular prediction, it's an outlier, and you don't know how far out, how often someone will achieve or fail to achieve the transmission you want based on the predictions of your configuration averaging. So this motivates us to try and look for methods that will improve our ability to offer information on how to design a system. Continuing on now with configuration averaging, I'll attempt to present some example results and also some different methods that others have used to attempt to improve on a method in the ways we want. So first of all, if we're looking for more than one variable, then as I've described, we gain surfaces in multi dimensions. Here we have a curve which is built in 3 dimensions, where we have plotted the average strength of the deltas against the number of deltas and the misfit between the configuration average with those quantities and our goal transmission. Now we can see from these curves that a minimum is attained around where we expect. This can motivate you in a few different ways. First, it's good to see that we do actually gain a minimum as we want. That's the only way we can actually use the misfit and configuration averaging. We need to be able to find a minimum. So that this space isn't flat is a good start. You can also imagine how this method can be used to improve on your results. Unlike with just throwing configurations into a database and looking for the minimum misfit out of it, by seeing the slope in this region, by looking at the overall geometry, we can imagine averaging the minimum in this region. So if we do not know exactly what our strength is, over the minimum region we average the number of deltas, and this can improve our confidence in a particular result. So that's just nice. That's a way to strengthen your results. Of course, this is about as far as you can go with this sort of visualization. With every new dimension, it's another dimension that would have to be graphed, and we can't do that. So for multiple dimensions, you do have to start thinking abstractly and working from there. Now, as we have mentioned, we do want to be able to extract as much information as possible out of our CA. And this can be achieved, and has been shown to be achievable by other members of the group, by being very clever with how you approach a problem. So, for instance, if we create a Sudoku-like puzzle out of our transmissions, so if we take our transmission across the top, I would take transmission on the right, etc., etc. We build up transmissions along different axes. We can then apply our configuration averaging and misfit to each of those transmissions to determine how many deltas or how many impurities we think there are in a particular region. So if we have 4 regions, but we are taking transmissions across multiple regions, we can actually, imagining Sudoku, through analogy to it anyway, we can apply a set of rules as a linear translation to return from our misfit for a particular side into the misfit, or into the number in a particular region. So this is just being clever, and it's getting us information about, it's almost a positioning of our deltas. You can imagine this isn't confined to 4 regions. You can further subdivide and subdivide, so you're limiting where you need deltas. So it's giving you positional information, which so far we've not seen any way to do that with configuration averaging. At least I've not presented any such ways. Additionally, all these methods are not limited to delta functions. This is a model we're working with because it's nice and you can learn a lot from a simpler model. But it's been seen, it's been shown by the group that configuration averaging, the misfit, all these inversion techniques, they work in multiple different regions. They're much more general than you might imagine. So we have seen results for delta functions. You can also achieve results for a square well, or for a chain of atoms. So here, that's just an example where this is not confined to a tie model. This is much more useful, or this has wide uses and is very applicable to other areas. Configuration averaging is an excellent method. It is fast, it's consistent. By being clever with it, you can achieve a lot more than you might originally expect. But if we want to be a bit more informative, if we want to, say, use a Bayesian approach to our methods, where based on our prior predictions about the system, we can give a posterior expectation, then we're going to use a method of Markov chain Monte Carlo methods. So in these methods, our goal is to have some prior prediction of what our quantities where our quantities can be drawn from. So for instance, we might just say that your placement of delta functions follows a uniform distribution. And then through our inversion method, we will try and give a new distribution which will produce, or is more likely to produce, the transmission we want. So this can take a number of different forms, might be unimodal, maybe bimodal, etc., etc. So each of these distributions will be for a single quantity, and that can be held for both position and for strengths. Handier again is, because of how the delta function system works, we're actually going to stop talking about position and more think about separation, because you can always translate the whole system, so that gives you the freedom to set one of your deltas to 0. So that just reduces the number of quantities we're looking for. So now we're going to look for the separation and for the strengths of each delta function. The main method we use, or the main algorithm we use, is known as the Metropolis-Hastings algorithm. So this has a few steps to it. So you make an initial guess. So this is your initial parameters for the system. You then vary this in some way, make some translation from that initial position. We then either accept or reject this new state with some probability. So this takes the form of a probability, which is the minimum of 1 and e to the minus beta delta misfit. So here we see the misfit appear again, multiplied by some temperature. So beta is just a temperature which tunes our acceptance rate. It's up to your choice. You'll mess around with it. If you didn't have that there, your acceptance rate would just be almost everything. So you want to have a lower but reasonable acceptance rate. And then our delta chi is just our final misfit versus the initial misfit. So to get that, we have to find the transmission based on these parameters, the transmission based on these parameters, and then get the misfit of each of them compared to our goal transmission. There are our main steps in Metropolis-Hastings. After that, we will take all our accepted states and build some histogram. This histogram will shape our posterior distribution. It will approximate it in some way, and we will then be able to check, does that distribution visually give a good match? We can use the misfit to give that quantity. For our pros, we get a lot of information back, a lot of information that theoretically we could give to an experimentalist, and they'll be able to reliably or more reliably produce devices with this particular sort of transmission. Additionally, you'll often see that your match, so your misfit, is lower based on these predictions than what your misfit for your configurational average is. So that means you're actually getting closer to the solution. But there's a few problems. As I mentioned, for each step in that process, we're getting a new transmission. Twice, actually. Well, once overall. We have our initial transmission, then we have a new transmission. We have to check each of these, compare every time. That adds up a lot because you have to repeat this process thousands of times to build your distributions, to gain confidence in your distributions. So the cost is very high. Potentially not as high as your initial cost for configurational averaging. But while configurational averaging is one-time cost, which you can use forever and ever without needing to alter, every time you apply this method, you're paying that cost again and again and again. And for more deltas, that cost rises. So it becomes problematic in that sense. We're also going to see a number of dimensionality issues. So for our problem, there's actually an issue to do with non-uniqueness, which is a benefit as well. A non-uniqueness is good in an inversion problem because it means you can make, or you can find a result without having to find their result. Sometimes two states will give the exact same transmission. And I'll try and illustrate that a little while. There's a few nice ways you can look at this. But that becomes a problem for Monte Carlo methods because you are probing an entire phase space. You can limit it somewhat based on what you know about the device. So you can say that it can only be so large. But you're probing a large space, and there can be multiple islands of equal likelihood, of like just as good. So your convergence can be messed up by this. So if we imagine each of these dots as a state that we check, so we move from one state to the next, we accept, move to the next, accept, and then we reject this state, but accept this state. There's a possibility based on the Metropolis-Hastings algorithm that neither of these states are better than this. In fact, this could be worse, but it's a probabilistic acceptance. So say this state was better than this state, that's always accepted. Whenever we're going to refuse a better state, but sometimes we'll accept a worse state. It's actually useful overall because it avoids you getting stuck in a region of local but not global minima. So it's important that we can do this, but because of a non-uniqueness, there's always a chance that we'll move to a worse state, and then on our next jump, we'll find a new minima, which might be just as good as this minima, but it has a whole new set of parameters, and these parameters are then going to even out our posterior distribution. So we're going to end up with something less informative, or at least something multimodal, and it's difficult to know when you're comparing all parameters against each other, which modes you want to be taking, which result will give you something without just messing up the whole transmission. Now, there are ways that you can minimize some of this problem. One particular way I took was I introduced a local updating to this. So with this method, I was able to, or the Monte Carlo methods could independently update the positions or the separations and the strengths. in a global updating system, both of those quantities have to update together. But by allowing them to be separated, you can actually gain improvements in this region without having to make a large jump. So that will actually increase your acceptance rate and it improves your predictions. But that necessarily greatly increases the number of transmissions you have to compute. And remember, your transmissions are all a system of matrix multiplication. It's something the computers can do quickly, but on a large scale, the time adds up. Now, if we just take a break from MCMC for a minute, I'm going to attempt to visualize these non-unique solutions as I've described them. And to do this, I'm going to look at the geometry of our misfit again. Specifically, I'm going to present these sorts of heat maps where red areas are quite large misfit. They're relatively large. They're not a solution, we can say that. Meanwhile, as you go down to blues, and then you have blacks and whites, these are all very close. In this particular example here, we are allowing positions to be known exactly. So we're just cheating a small bit to limit the amount of information we need. And on these axes, we are plotting the results for the strength of each delta changing. So we see on the left that the position which is known and the strength, we have the same strength for each delta. We have 5 and 5. So then clearly 10 and 10 is bad, 0 and 0, you've no deltas at all. It's not a good match. But then as we move up towards 5 and 5, we have this absolute minimum. It's 0, it's a perfect match. We also see that on either side, so for a small move, we actually have 2 very good matches as well. And this is along the axes of average equal to 5. So we are able to see that our average can get, or if our delta functions on average produce the same overall strength, we can get pretty close. But this stands in a very small area, it's very close together. Now, if sticking with the same positions, we have strengths which are both different and further apart, we now actually increase the region of low misfit, so there's an overall better match actually. But even more interestingly, we find 2 regions corresponding to 4 and 2 and to 2 and 4, and both these regions are 0 misfits. They're both completely equal, the exact same transmission. And this tells us that specifically for 2 delta functions, you can actually swap the delta functions and receive the same transmission. But that's all on non-uniqueness when it comes to strength. That's like, there are cases where you get some non-triviality, but overall the region is it's a strong gradient. It's very clear where our minimum is. So this is something we will expect to be very easy to navigate for Monte Carlo methods. Now if we allow strengths to be known, and instead we are searching for position, and instead we're actually going to look for the separation, which is equivalent, really. Just means we reduce the number of axes here. So we have the separation between the first and the second delta, and the second and the third delta. And in this, I tell you, this geometry, we actually find an ellipse forming, where each of these dots are equally good transmissions. They are all results. Each of these dots is an equivalent result. So this is useful for an inversion problem, because it means we don't have to worry about the answer, or at least we don't actually care what the answer is. We care about what the transmission we get out at the end is, as long as the transmissions match. And for any of these dots, our transmissions will match, even though they're multiple solutions, which it's just a very nice freedom we have in inversion problems. Unfortunately, this is also a bit of a hindrance for us when it comes to design, or at least in how we're approaching design for HMC here, because as I illustrated previously, we are able to move towards a particular minima here for a long time, get a lot of results around that minima, and then we could suddenly shoot off to a completely different region and start looking for a new minima again, and our data will potentially be seen to kind of flatten out. It would become, our result would be, or at least our distribution at the end would seem less useful. It would almost be, it would potentially look quite uniform. This is simply, it's going to be an issue. It's going to result in scaling issues. The more variables we have, the more of an issue this is. It just, like, the best solution is to run the program more times, get more data, and you're probably going to settle in towards a minima. And even if you get a bimodal distribution, because it's non-unique, you're getting a similar transmission out of them. But it will become an issue. It will result in a reduction in our acceptance rate in our HMC or our MCMC. If we can limit this, we can greatly improve the method. But now we can return to Markov chain Monte Carlo, and I want to try and run through the process. I want to show how we'll use this in inversion or design. So we start off with our goal transmission. This was step 1 when I began. So we've a transmission here, and this has been generated by 3 delta functions. Our separation and strengths can be seen here, but we will pretend that's unknown. This is not information we actually need. It's not needed for the process. All we imagine having is this transmission, the data behind that. That's all that's needed, just to compare against that. So we've run Monte Carlo, and we've used an uninformative prior. We've basically allowed both strengths and separations to be drawn from a uniform distribution. So in an uninformative prior, it's just a flat line really for any particular parameter. But at the end, we actually have produced what look like distribution functions for each individual parameter. So for the strength of the second delta, and for the first and the last, we have produced 3 different distributions, and each of these distributions have a mode, a most probable result, which we indicate with this red line here, and we've also plotted what the true result is, what the actual strength, or what that actual strength is. So that's the yellow line on these graphs. And we visually see that the mode, it gets fairly close. It's not on top of it. It can be, but it's not in this case. But it's close. It's certainly within standard distribution. If we then move on from the strength and look at our separations, we see something else entirely. So first of all, we have very sharp peaks here. Very sharp peaks. So this indicates to us that our model has quite a high degree of confidence in these particular modes. It believes that they are very likely to produce our result, the result we want, the transmission, our goal transmission. But this looks unlikely because our true probabilities they're not near our modes. They're not close. They're not close. And they're also not a permutation. If we actually look at these graphs, we haven't just swapped our results as you might expect at first sight. They're just completely different. So this might begin to worry you looking at this. It seems that the method has gone off the rails. It's given us some high degree of confidence in both our results. It seems to think it has landed on the correct separation, but it's not near a true separation. But we remember non-uniqueness. Maybe non-uniqueness saves us. Maybe here we haven't found the original configuration. We found an equivalent configuration. So now we check that. We will produce a transmission from our mode result, our most common result. So we take the mode of each parameter and check what transmission that results in. It looks pretty close to me. So here, our blue line is our true transmission. The orange curve is our probable transmission. And then just to add in, that red line there is our CA. And visually, it looks pretty good. It's definitely not perfect. Our range is a bit off in places. We have some peaks for the blue curve that are not hit by the orange, and the orange seems to dip lower in some places. But I think it looks like a pretty good match. It seems to be oscillating at a pretty similar rate. And if we quantify this numerically just by taking the misfit, we will actually state that the misfit for the most probable solution, our Monte Carlo solution, is on the order of 0.008, whereas our CA is 0.027. So we've got an order of magnitude improvement by using MCMC. And in addition to that, we have a distribution, not just a set of values that gives a close match, or that on average gives close match. We've actually given a distribution that we argue will tend to give us a very close match. In addition, we can gain a bit more. We can squeeze out a little bit more information from these distributions. Here we've produced a corner plot, and on this we will have separation 1 and separation 2. So these top two distributions, and here we've used a process of kernel density estimation. It's a fairly standard method in these sort of statistic approaches. It's normalized the data, it's attempted to extrapolate what the actual distribution function would look like. Then we have strength. And so they're what we had, they're what we produced from our histograms. But we can also look at how each of these distributions are correlated. So here we actually see a very strong correlation between our two separations. This line actually tells us that what one separation is has a strong influence on what the other must be. And our separations always appear to have a very strong influence, so, or at least an influence. So we don't see as strong a correlation between the strengths and the separations, but there's definitely some non-trivial correlation occurring. But then in the regions where we are just comparing strengths to strengths, we see it's actually fairly little correlation overall. There is some, of course, maybe you're attempting to tune something here, but hardly any correlation compared to the correlation between separation. This is all kind of a nice to know. It's potentially useful, and it's good to see that we are gaining a lot out of our MCMC approach. But there are problems. In our previous example, that demonstration of MCMC, where we had 3 delta functions, just for reference, the acceptance rate, so this is how many of the transmissions we tested were accepted, was about 2%. And this is beginning to get problematic because those distributions we gave, they were from histograms. They clearly need a lot of data. And obviously you want a lot of data just to have any degree of statistical confidence. But 2% is low. And that will drop again and again very rapidly as the number of deltas increases, because the number of deltas increases the number of variables we're searching for. And we once again, non-uniqueness, dimensionality expands, the acceptance rate drops, and that harms our ability to produce good distributions
potentially you just run your code for longer. But this is becoming an exponential problem right here. How many deltas is an acceptable number to cut off? It's a question. Maybe instead of just increasing the number of transmissions, we can attempt to look at different methods that will maybe not suffer as much from dimensionality. One method I dipped my toe in, I had a quick look at, was Hamiltonian Monte Carlo. So this is a method that it kind of builds on Metropolis Hastings' algorithm, but it's making use of a kind of idea of energy conservation where we use a fictitious momentum to move around our phase space. I implemented this. We're only looking for strengths. This is an easy problem. I want to make that clear. The positions were known. It becomes much more difficult when the positions are not known. But just as proof of concept, maybe something to look at further, we can see that this does work. In principle, we can use HMC for searching for what our strengths are. So once again, blue is true, orange is our probable solution, because HMC, still produces distributions. So this is the probable distribution based on the mode of our distributions. And then the red line is the CA for this particular transmission. Once again, prob is on the order of 0.004 and CA is on the order of 0.056. We've improved on CA, we have distributions, it looks nice, but there are still going to be issues with HMC. To use it, you have to look for the gradient of our misfit function. This is non-analytical as you approach it, so I used finite difference methods to get the gradient. That's again going to scale terribly with dimensionality. You are almost running into, if we want to use this method, we would want to be using a supercomputer to distribute our calculations. We can then conclude this talk with just a quick look at what we've gone over. So our goal with this talk was to look at inversion methods and design using a delta function model. To this end, we looked at the methods of configurational averaging and Markov chain Monte Carlo, and also a bit of Hamiltonian Monte Carlo, to attempt to both invert our problem. So we've taken a transmission and we've attempted to find the parameters which will produce that transmission on demand. And with these methods, how we can aid the design of different devices to produce any particular goal transmission. First, we discussed configurational averaging. And we saw that CA has a initial cost quite strong, so it's quite large, but then it's negligible after that. So any additional time, it dies off early. Yeah, the more times you use this, the less you need to worry about your time cost. I don't want to pretend the initial one is not to be worried about. You can spend a very long time producing CA, particularly if you want to produce many averages for every state, and also if you want to check a large number of states. For every new delta function, there's another matrix multiplication, which is definitely not instant. It adds up over time. And you have to think, you want to check multiple positions, multiple different strengths, arrangements of strengths, etc. So there, it is a very high initial time cost if you want all that detail. After that, if you are planning to use this tool for a long time, then it begins to seem very worth it, because it is very quick after that. You can also get around some shortcomings about averaging and the information that that gives you by being clever, as we've shown. But it does seem a bit specific at times, and for that we looked at MCMC. And this doesn't exactly come with an initial time cost. You just take your goal transmission and then you check based on that. But this cost increases and increases and increases time ever onwards for every new variable you have. Overall, you can appreciate the information you receive from MCMC. I think it's very useful to have distributions. It would absolutely aid design a lot. But that time cost is problematic. Very large time cost. It becomes a judgment at the end of the day. That's all you can really say. If you can work with CA, if that gives you enough, don't look at anything else. CA, great for that. If you could think of a clever way of using CA to get more information, probably use that. But if you do want to look very closely at a specific problem, just once or twice, then MCMC, it seems like it's definitely something worthwhile, I would say. Thank you very much for listening, and I want to give many thanks to Professor Mauro and to all the members of the theory and modelling group for all the help over this summer. And thanks to Daniel Barron, the TPSA video coordinator, and TPSA for hosting.